Hey everybody. Today we're covering the chain rule. The chain rule is a way of differentiating compositions of functions, things of the form f of g of x. For instance, we might want to differentiate the square root of x to the fourth plus 4. Here we have an outside function, the square root of x, and an inside function, x to the fourth plus 4, both of which we can differentiate. Or we might want to differentiate 1 over 1 plus 2x plus 6x squared. Here we have an outside function, f is 1 over x, and an inside function, g, is 1 plus 2x plus 6x squared. Again, we can differentiate both of those pieces. How do we differentiate f of g of x in these situations? Well, here's how. The chain rule says that the derivative of f of g of x is f prime of g of x times g prime of x. Basically, what we're going to do here is work from the outside in, differentiate the outside function, plug in the inside function exactly, and then multiply by the derivative of the inside function. Now, of course, in order for this to work, g has to be differentiable at x, and f has to be differentiable at g of x. I think the chain rule makes a lot more sense when we start working through examples, so let's jump right in. Let's take care of the two problems we saw in the previous slide. The derivative of the square root of x to the fourth plus 4. We're going to start by rewriting that square root as a 1/2 power. Here we have an outside function that's the 1/2 power, and an inside function of x to the fourth plus 4. We differentiate the outside function, so something to the 1/2 is going to be 1/2 times the something to the negative 1/2 power. And then we multiply by the derivative of the inside function to get 4x to the third. Simplifying a little bit, we get a final answer of 2x to the third over the square root of x to the fourth plus 4. Next, let's differentiate 1 over 1 plus 2x plus 6x squared, also known as 1 plus 2x plus 6x squared to the negative first. Here, the outside function is the negative first power, and the inside function is 1 plus 2x plus 6x squared. The derivative of that negative first exponent is going to be negative blah 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 to the negative second. And then I multiply by the derivative of the blah blah blah. So, simplifying this a little bit, I get negative 2 plus 12x over 1 plus 2x plus 6x squared to the second power. The chain rule is particularly easy to remember in Leibniz notation. If the outside function is y and the inside function is u, then the derivative of the composition can be written dy dx is dy du times du dx. I think this is particularly easy to remember because it looks visually like the du's should cancel. Of course, these aren't actually fractions, so that cancellation doesn't literally make any sense, but it sure does help when I'm trying to remember this. Let's do a problem that's explicitly using this perspective. Suppose y of u is u squared minus 2u plus 5, and u of x is 5x minus 1. So y of x is 5x minus 1 squared minus 2 times 5x minus 1 plus 5. So dy dx is going to be dy du, 2u minus 2, times du dx, which here is 5. We can rewrite that as 10u minus 10. Now, y is a function of x, so I would like my derivative to be written in terms of x only. Let's take out u and replace it with 5x minus 1. Simplifying that a tiny bit, I get a final answer of dy dx is 50x minus 10. Of course, the chain rule can be combined with the product rule, the quotient rule, and other instances of the chain rule. So we're now able to differentiate a much greater variety of function. Let's do a few examples differentiating more complicated products, quotients, and compositions. First of all, let's differentiate 2x minus 7 to the fifth times x to the third plus 2x minus 8 to the fourth. Here we have a product. We're going to need a product rule. And each of the component pieces is going to require a chain rule. 2x minus 7 to the fifth, and x to the third plus 2x minus 8 to the fourth. Remember, to differentiate a product, fg, you do f prime g plus fg prime, the derivative of the first times the second, plus the first times the derivative of the second. So, let's differentiate piece by piece. The derivative of the first, using the chain rule, is 5 times 2x minus 7 to the fourth, times 2, 2 here being the derivative of the inside. Then I multiply that by the second function, x to the third plus 2x minus 8, all to the fourth. Then I add the first function times the derivative of the second, so 2x minus 7 to the fifth times the derivative of that second factor. The derivative of the second factor, using the chain rule, is 4 times x to the third plus 2x minus 8 to the third, times the derivative of the inside, 3x squared plus 2. Next, let's differentiate a quotient that uses the chain rule. Derivative of the quantity x to the fifth minus x to the seventh, all to the third, divided by 5x squared. Remember how we do the derivative of a quotient? Low d high minus high d low, draw the line and square below. So, we take the denominator, multiply by the derivative of the numerator, which we have to do using the chain rule, 3 times the inside squared times the derivative of the inside. Then we subtract the numerator times the derivative of the denominator. So x to the fifth minus x to the seventh to the third times 25x to the fourth. Then we divide that entire numerator by the square of the original denominator. That's where the 5x to the fifth quantity squared is coming from. We could simplify this, but I don't think it's really worth our time to do so. Instead, let's do one final example. Let's differentiate the cube root of the quantity x squared minus 8x plus 1 cubed plus 5. Let's rewrite that cube root as a 1/3 power before we differentiate. Okay, so we have an outermost function, that 1/3 power. Then we have a next most inside function, which is the cube plus 5. And then finally, we have an innermost function, x squared minus 8x plus 1. The rule here is we should differentiate from the outside in. First, we differentiate the 1/3 power. We'll get 1/3 times everything inside of that 1/3 power to the negative 2/3. Then we multiply by the derivative of the inside of that bracket. So I'm differentiating quantity x squared minus 8x plus 1 to the third plus 5. So I'm going to get 3 times the inside of the parenthesis squared times the derivative of the inside of the parenthesis, 2x minus 8. Once again, I don't really think it's too worth our time to try and simplify this at all. We'll call this a final answer.